Hi folks, in this lecture I will cover the method of dealing with data that looks like maybe it has a problem. That isn't to say that the data is no good. All data is essentially good data in that it can be instructive, but we do need a way to quantify well-behaved data from aberrant data. So welcome to Lecture 5 online. Under Measurement Problem and Debug and Improvement, this is something that's called Chauvenet's criteria. And you'll have some homework at the end of this to do with it. I cannot give an extensive presentation of the derivation of this statistical method, the Chauvenet's criteria, but there are circumstances when an engineer finds bad data. Okay, maybe I mean this kind of data instead. I'll try it again. The circumstances when an engineer finds some data points that look suspect. Does that make more sense? Okay, so when faced with this, it becomes the task of an engineer to decide if the suspect data points are either the result of some gross blunder and can therefore be neglected, or are indicating some new type of physical phenomena that is peculiar to the certain measurement or operating condition. In short, we cannot simply throw out the data points we don't like. We must use a consistent basis for discovery and then possible elimination. Enter Chauvenet's criteria. So, William Chauvenet, born 24th of May, 1820 in Milford, Pennsylvania, and died December 13th, didn't quite make it to Christmas, 1870 in St. Paul, Minnesota. So let's see here, 1870, 1820, 70, 20, 50. He was 50 years old, all right? So in that time, he was a professor of mathematics, professor of astronomy, professor of navigation, and a professor of surveying. He was instrumental in the establishment of the U.S. Naval Academy in Annapolis, Maryland. And later, he was the second chancellor of Washington University in St. Louis. Okay, so after his death, the Mathematical Association of America established a prestigious prize in his honor called the Chauvenet Prize. The Naval Academy has named the mathematics building that every midshipman goes through after him. And the Navy christened 2 ships after him. And there's a crater on the moon named after him. Okay, so if this guy isn't a STEM stud, I don't know who is. The idea behind Chauvenet's criteria is that there is a band of probability centered on the mean of a normal distribution that should reasonably contain all n, that's lowercase n, samples of a data set. Any data points from the n samples that lie outside of this probability band can be considered to be outliers and can be removed from the data set. Now his method then directs you to recalculate the new mean, recalculate the new standard deviation based on the remaining values and the new sample size, and then once you've got that, you move on. Your homework will give you a chance to practice this technique. And the technique presented here works for all scalar values, all scalar data. Now recall a scalar. A scalar is a value, it's a number that's referenced to something. For example, scalars can be integers or real numbers that scale something like weight, distance, temperature, mass. You fill in the blank measurement, right? It's exactly the sort of number you would encounter in a class about, well, metrology. So you have a graph here. I've presented a graph of distribution. And let's say you've got a group of data that you've measured the stiffness on. And you also have a second measurement you've made density. So you've got 2 distributions. And you want to plot stiffness against density. Well, first, you'll run Chauvenet on the stiffness values. And you'll run Chauvenet on the density values. And you would do that before you would plot stiffness as a function of density to make sure there were no outliers. Now the outliers are calculated by using the number of standard deviations that correspond to the bounds of the probability band around the mean. That's a lot of words, right? Essentially, it's Chauvenet's criterion table. He's already helped with this, and we'll go through that in some detail. And then you compare the value from the table to the absolute value of the difference between the suspected outliers and the mean that you've got, your population mean, divided by the sample standard deviation. Okay, lots of words here, but we'll go through it and you guys will get it. All right, next slide. Okay, so quite simply, here is the criterion table that was developed by Chauvenet. Looks simple enough, I think. Chauvenet's criteria specifies that a reading may be rejected if the probability of obtaining the particular deviation from the mean is less than, well, 1/2 n. The table presented here lists the values of the ratio of the deviation of a particular value or measurement to standard deviation for various values of n, so according to the criteria. So the number of readings you've made, the number of parts you've got in your database, right? That tells you what the precision index can be, how much shift you can have before you say, you know what, that part's no good. More simply, if the ratio of the difference for any reading from the overall mean of big capital N readings, when divided by the standard deviation of the population N, is greater than the maximum so-called precision index number, then the value in question is considered suspect. It's shifted too far. So let's say you've measured the distance of a football field using a tape measure, and you do this 25 times. This means n equals 25. The precision index is 2.33, which means that the deviation or difference from the mean for any single measurement, when divided by the standard deviation for all 25 measurements, cannot exceed 2.33. It's interesting to note that the more measurements you take, the bigger n becomes, and the more forgiving the precision index value becomes. So we will run through an example, though first we've got to do some discussion about some formula. All right, let's step through these, equations 1 through 7. Number 1, this is the criteria given to us by William Chauvenet and his precision index table. That was in the previous slide. Number 2, this is the deviation ratio for each measured value. So if we took 25 measurements, then we will calculate 25 deviation ratios. Note too that it is the absolute value of the deviation ratio, d sub I divided by sigma. Number 3, now this is the old school nomenclature for the calculation of arithmetic mean. It's what your calculator does when you hit mean, right? A little button. Or in this case, it's the average of all measurements. Number 4, this is the deviation d sub I, and it is the individual measurement subtracted from the population mean. So for our example, the football field, we will perform this math on all 25 data points. Number 5, mean square error. This is the old school method that constructs the building blocks for the calculation of variance and standard deviation of the population. Number 6, well, this is the sample standard deviation equation. Again, it's old school. It's the mathematical formula that resides behind that button on your calculator. You should be able to calculate standard deviation using the formula eschewing that little button. Number 7, finally, we have the percent difference calculation. We'll use this when we look to see the results of eliminating a potential outlier data point. In this example, we are developing a prototype process to produce a variable force absorbing mat. The goal of the mat is to maintain a certain height range or vertical deflection independent of a distributed force across the mat within a certain range of force. The mat must be capable of maintaining the force-height relationship for any 10 centimeter diameter disc across the entire pad. So you see pictured here a test setup where a 10 centimeter disc is pressed against the pad to measure for a given force, and contact area, and related to that will be the vertical deflection. So let's take 10 measurements across the face of the pad to see if we find a consistent relationship. So let's break down this table. Break it down! In the first column, listed as reading, This represents the 10 serial numbers for each deflection, the 10 deflection readings we took in millimeters, 1 through 10. In the second column, we see then the range of readings we took, from a high of 6.77 millimeters to a low of 4.33 millimeters. And at the bottom there is the average reading, 5.613. But I see, Professor Bonner, too many sig fig. I know. But it's an intermediate calculation, and we know as long as it's an intermediate calculation, we can carry a few extra sig fig along, as long as we realize at the end we got to go back to the appropriate number of sig fig. So just don't overdrive your headlights here. The next column we then have is d sub I, where we list the deviation of each individual reading from the average, the mean of the 10 sample population, which was the 5.613. It's the difference. Next column then is our mean square error column. Remember, this is a usual and typical component of the standard deviation calculation, but heck, we calculated deviation, so mean square error is super easy to calculate. The final column then is our test statistic d sub I divided by standard deviation. Of course, you will need standard deviation, and that can be calculated either by using the standard deviation button on your calculator, with the range of measurements we took in column 2, or you can add up all of the mean square errors, divide by the degrees of freedom minus 1. It was 10 data points, so 10 minus 1 is 9, so divided by 9. And then we take the square root of that variance to obtain standard deviation. All right, so let's pull out Chauvenet's precision index here, and we see for n equal 10 readings, our limit is 1.96. Now we look at our 4.33 value, and it's suspect. It's suspect because it falls outside of the reasonably expected range for normal distribution data given the standard deviation of the data. Recall, it's the probability linked to the expected results. So recall, we checked against the maximum allowable criteria at n equals 10, and it was a precision index of 1.96. We saw that reading 5 exceeded that criteria, so something happened to reading number 5. So statistically, we can remove reading 5. And you can see reading 5 is no longer in the table. So the technique then allows the practitioner to eliminate the suspect data point, which we did, and recalculate the mean and standard deviation from the group, making the assumption, right, that you won't forget about it and simply move on. You need to go back and see what happened. So then we recalculate the mean and the standard deviation for n equals 9. And we go back again and look at Chauvenet's precision index. Do you notice something out of whack again? What about reading number 3, the 6.77 value? What does our criterion say about that? Well, for n equals 9, the limit is 1.91. And we see the criteria, our test statistic is 2.19. Does this cause some discomfort? Well, it should. Let's finish the calculation stuff first, and then I will cover this discomfort that you should be feeling in the discussion. Okay, so we see the first time through our calculation with all 10 data points, we achieved a mean of 5.613 millimeters and a standard deviation of 0.6266 millimeters. And I know, Professor Bonner, too many sig fig. I know. Just hang with me here, okay? So, we uncovered a suspect data point. It was 0.5, and we statistically set it aside. We didn't forget about it. We just statistically set it aside. And once doing that, we recalculated the mean and the standard deviation. Now, the mean changed very little. There's probably essentially no impact on bias. That's cool, right? And we also reduced the standard deviation by like 25%. The measured reduction in variation. That's fabulous. But if you're running to work to improve a process and find a boneheaded error in your measurement, then surely discovery and elimination of a truly bad data point is a no-brainer, especially if it has no impact on bias and helps you better target your information. But what about our test data here? We're looking to see that we had a consistent deflection over our entire variable force absorbing mat. Did we achieve this? So, is it a boneheaded measurement error, or is there a soft spot in the mat? And when we saw the second round of calculations, where we uncovered another suspect value, this time on the high side, what might you consider as your next step? Do I have hard spots and soft spots in the mat? Do I look at parts? Do I look at process? Consider this week's lecture, and from there, be prepared to answer a question like this on your homework. So all measurements that deviate from the mean by more than the maximum allowable deviation ratio, the precision index, right, for a given number, n, they can be rejected. However, they can be statistically rejected. However, statistical outliers may be significant. They may be instructive in terms of the physical phenomena being studied or measured. And they could aid in detecting flaws in the experimental or measurement technique. In the situation where we find that a value exceeds the ratio, we may be tempted to simply discard the values on the basis that something surely must have gone wrong, and then just say move on. However, that would be a mistake. Chauvenet's criteria also may be applied only one time to a given sample of readings. You can't do it over and over and over and over again. Only once, right? You may lose 2 or 3 measurements in that one time through because they exceed the ratio, but you can only do it once. And then no further application of the criteria to the sample set is allowed. Now we redid the calculation. You want to do the calculation a second time because you may discover a problem, right? If there are data points that continue to exceed the criteria, like we found in our example, then it is time to stop and do a deeper dive on the entire measurement process. Never ever just throw away data points. Bad data is instructive data. Dig and find out what happened. Well, it's happened again. You've wasted another perfectly good hour of your lives listening to car talk with Click and Clack, the Tappet brothers. Oh no, wait a minute. This was a lecture. Hey, this was good stuff. So, look, you will find homework associated with this lecture on Blackboard. I also brought a hard copy to class. It's due the next time we meet. All right? So questions, do let me know. Otherwise, good luck and see you in class.